Hi people, I'm working on understanding the dynamics of collaborative knowledge building in crowdsourced environments. In this presentation, I'll be talking about the existence of ecosystem in crowdsourced environments. Before I start, I would ask you a question. These days, whenever you have any question, be it a technical question like a question on the operating system that you're using or the programming language that you're working on, or be it any non-technical question like a question on countries, cultures, etc., where you get answers to your questions. I'm sure you would say that you write your question in Google and then Google directs you to certain websites, and that's where you find an answer to your question. Now the point is, which kinds of websites are able to answer your queries? Are these websites which are run by an expert or a group of experts who have done some extensive work in that area, and that's how you're getting an answer? The fact is that most of the times we get answers through websites like Wikipedia, Stack Overflow, Quora. Now we know that these are the websites which are not run by experts. Rather, anybody who is online is contributing to the knowledge building process on these websites. In fact, even apart from experts, even the non-experts are participating in the knowledge building process by, for example, asking their questions. Now let us compare this scenario to what used to happen, say, around 10-15 years back. The time we used to go to libraries where we would look through some books, and in a book which we thought could probably answer our question, we would look through the index which led us to a page which sometimes used to answer our queries and sometimes not. These books were written only by experts, and that's how the knowledge building process was taking place in that era. Whereas these days anybody can participate in the knowledge building process. Anybody can edit an article in Wikipedia. Anybody can ask a question on Quora and Stack Overflow, and that's how they're contributing to the knowledge building process even while they are non-experts. So we can see that the knowledge building process has completely changed. As another instance, why is it that the knowledge in Wikipedia, which is written by common people, has already surpassed the knowledge of Britannica Online, which is written by only experts? To further look into the transition that has taken place in the knowledge building process, I would like to share an anecdote with you. Four-color theorem, which is an important mathematical problem, it was proved by Kemp in 1879. It was a proof which was consisting of 8 pages. Now this proof was well accepted by the mathematicians community until it was disproved 11 years later. Now let us talk about another important mathematical problem, which is an open question even now for theoretical computer scientists. Is P equal to NP? There was a serious attempt to prove this conjecture in 2010. This was a proof which consisted of 100 pages. This proof was disproved by the mathematicians community in less than 10 days. Now the question is, why did it take 11 long years to disprove a proof which was 8 pages long, whereas it took less than 10 days to disprove a proof which was 100 pages long and full of technicalities? Now the point is, in the second case, mathematicians made use of a portal which is called Polymath Project, which started as a blog in 2009. The mathematicians across the world collaborated over this portal, read the proof line by line, gave their insights, and that's how they were able to disprove this long proof in such a short span of time. So the point is, what has led to this acceleration that has taken place in the knowledge building process? Of course, the developments which have taken place in web technology are responsible for it. So before we look into the exact reasons behind the acceleration in the knowledge building process, we'll quickly take a look at the versions of web. Experts say that there are 3 versions of the web: Web 1.0, 2.0 and 3.0. They also say that currently we are in version 2.0 and we are swiftly moving towards version 3.0. Web 1.0 was a version which made use of tools like HTML, FTP. We can think of it as a library which we could use as a source of information, but we could not change it or we couldn't contribute to it in any way. The best example is Britannica Online. Web 2.0 is a version which is making use of tools like Python, PHP. Now here we can read from the web pages as well as we can write onto it, we can collaborate with others. So we can receive the information as well as we can contribute to it. The best example is Wikipedia, Facebook. Web 3.0 will make use of tools like rich description framework and web ontology language. People believe that Web 3.0 browser will act like a personal assistant. As we search the web, the browser learns what we are interested in. The more we use the web, the more the browser learns about us, and the less specific we'll need to be with our questions. I'll quickly give you a small example to understand how Web 3.0 is perceived to be. Assume you have decided to go see a movie and grab a bite afterwards. And further assume you are in mood for a comedy movie and some Italian food afterwards. You start your PC and open your web browser and head to the Google to search for theater, movie and restaurant information. You need to know which movies are playing in the theaters near you. So you spend some time reading short descriptions of these movies before you make your choice. Also, you want to see which Italian restaurants are near to all these theaters. You would also like to see the customer reviews for these restaurants. So in total, you visit more than half a dozen websites before you're ready to head to the door. Web 3.0 is perceived to make searches like these easier and faster for us. For example, you might be able to type a complex sentence or two in your web browser and the web will do the rest. For example, in this case, you could type, I want to watch a funny movie and then eat at an Italian restaurant. What are my options? The Web 3.0 browser will analyze your response, search the internet for all possible answers, and then organize the results for you. So it may also happen that if you and me both write the same query in our browsers, you might get different results and I might get different results. That will happen because our browsers will become personalized. They will give results based on our past searches. All this will be possible because web will take the form of semantic web, where web pages will consist of extra information in the form of ontologies. An ontology is a file which will consist of metadata about the terms which are used on that web page. So that was a glimpse into the possible future of the web, which will directly affect the knowledge building process as well. Now let us take a look at how knowledge building is taking place these days. Knowledge building these days is taking place through a technique called crowdsourcing. Now what crowdsourcing is? We all must be knowing what outsourcing is. It's a technique in which a company gets some work done by some other company. On contrary, in crowdsourcing, we get some work done by the people in the crowd. Now what does the crowd consist of? In the context of online portals, crowd consists of anybody who is online. It consists of general people who could be experts or they could be non-experts as well. So crowdsourcing is the process of harnessing the collective wisdom of the crowd. Over the last decade, crowdsourcing has gained immense popularity in the area of learning and collaborative knowledge building. The best examples for crowdsourced websites are Wikipedia, Quora, and Stack Overflow. Most of our Google searches give Wikipedia as the first search result. Whereas Wikipedia is based on the wiki technology, which allows users to not only have access to its content, but also to change the content online. Quora and Stack Overflow are based on the discussion forum technique. An increasing number of communities are benefiting from using these crowdsourced portals in order to learn new things. While crowdsourcing-based platforms are on a rising scale and rapidly accumulating knowledge, the dynamics of knowledge building in such environments is an area which is relatively unexplored and not very well understood. For example, how do people collaborate to build knowledge? How is it that such portals based on crowdsourcing are able to build knowledge from such a vast group of people across different domains? Is it so that people contribute better when they collaborate? And if that is so, then what are the reasons behind it? The aim of this work is to understand the dynamics and the properties of this collaborative process. To do our analysis, we needed some data. And for that purpose, we created a customized crowdsourced portal. Now, what was the portal and why was it built this way? There is a motivation behind it, and I'll share that with you. Let me ask you a question. Assume you have to read a book. On one side you have a book which is fresh, new book, and on the other side you have a book which has been read by somebody, and that somebody had this habit of underlining, highlighting the important concepts, and writing his own insights in the margins. You have to assume that the book is difficult to understand for you all by yourself. So in that case, which book out of these two would you prefer to read from? Now, given that the topic is difficult for you to understand all by yourself, I'm sure you would agree that instead of a plain new book, you would prefer to read from a book which has been annotated by others, where annotating means that some comments have been added in the document margins, some sentences have been underlined, some parts have been encircled or highlighted, some stars have been put at various places. This is because it lets us know some other person's perspective on the text under consideration. We get to know some extra information about the text that we are reading. Also, we get to know the points where other people got stuck. Keeping this intuition in mind, and in order to have a playground for our research, we built an annotation system which we call Crowdsourced Annotation System. This is a snapshot of the Crowdsourced Annotation System, CAS. As you can see, it shows two parts. On the left hand side, there is this document which is to be read and annotated by the students. On the right hand side, there is this panel which is called Annotation Panel. Any text document can be uploaded to the portal and the participants can be authorized to access it. Any part of the document can be annotated by selecting the corresponding text on which a pop-up box appears in which the annotations can be added. The annotated text of the article is shown highlighted on the interface. When the user clicks on this highlighted text, the corresponding annotations appear on the right-hand side panel. We observed the type of comments that users usually add on an annotation system and found out that they either ask questions, or they answer others' questions, or they add their own insights about the given text, or they give some reference to some external resource which is relevant. Based on this observation, we incorporated one more feature into CAS, and that was, while adding the annotations, CAS provided the users to select the type of annotation that they were adding from a drop-down menu. The options that the menu provided were Q for question, A for answer, I for insight, and P for pointer. Q&A type of annotations were useful in creating a dialogue between the annotators. The annotators could add any extra information about a part of the content by making use of I type of annotations. P type of annotations could be used to point to a similar and useful content on the web. In order to do our analysis, we conducted an experiment on CAS where 60 students participated, and the aim of the experiment was that the students had to read an article, and in the process of understanding this article, they had to keep annotating wherever they found it useful. The article that was uploaded was Randomized Closest Pair Algorithm, which was chosen carefully for this experiment because it was less straightforward and mathematically very involved, and the students were less likely to understand it by independent study. This is some of the statistics from the experiment. After taking note of the IQ and P's percentage distributions being 24%, 19%, 52%, and 5% respectively, one would infer that most of the users mainly expended their effort in posting A type of annotations and secondarily on I type of annotations and then Q type of annotations and finally on P type of annotations. In order to observe whether this was true or not, we created a 4 tuple for every user, where the members of this tuple were the normalized distributions of the effort that they made in the categories I, Q, A, and P. For example, if a user posted 10 annotations each in all the 4 categories, then his distribution will be 0.25, 0.25, 0.25, and 0.25. Similarly, if a user posted 10 annotations in I category and no annotation in Q, A, and P category, then his distribution will be 1000. So this distribution tells us the relative effort that he made in the various categories. After computing the distributions for all the users, we created a plot where x-axis denoted all the 60 users and y-axis denoted their effort distribution in all the 4 categories. Now, going by our previous intuition, assume all the users spent almost equal time in posting A type of annotations. What do you think will be the plot that we'll be getting for A type of annotations? We would be getting a line which is almost parallel to x-axis. But this was quite in contrast to what we observed as per our logs. As you can see, the figure denotes the distribution of I, Q, A and P for all 60 users. There are 4 dots colored blue, red, yellow and green denoting the I, Q, A and P distributions respectively for individual users. The yellow dots represent the effort distribution that was made in A category. As you can see that the yellow dots are unevenly scattered and are not clustered along any line parallel to x-axis. This is true for red, blue and green dots as well. This indicates that the amount of effort that various users spent in the 4 categories was not equal. Rather, some spent more time in questioning, some in answering, some in posting insights and some in posting pointers. To further analyze this behavior, we prepared 4 lists, each for I, Q, A and P. Each list consisted of the users sorted in decreasing order of their contribution in that category. That is, the top user in category A was the one who posted maximum number of annotations in A category as compared to all other users, and so on. Similarly, the last user in the list A was the one who posted the least number of annotations in A category as compared to all other users. Now, K is equal to 1 means take top 1 user from all the lists, which gives us 4 users. Now, what do you think will be the number of common users in this list of 4 users? If there is a user who is the topper in answering as well as questioning, then his name will appear twice in the list. If different people are specialists in different categories, we'll have no common user. As we kept increasing the value of K, we kept taking a note of the number of users who appeared once, twice, thrice and 4 times. We called a user K Unispecialist if he appears in the list of top K contributors for precisely one type of annotation and doesn't appear in the top K of the other 3 types. Similarly, if a user appears twice in the list, we call him bispecialist. If a user comes thrice in the list, we call him trispecialist. And if a user comes 4 times in the list, we call him quad specialist. So what we did was we kept increasing the value of K, and for every value of K, we calculated the number of uni, bi, tri and quad specialists. The figure shows a plot of the number of uni, bi, tri and quad specialists with x-axis running through K is equal to 1 up to 18. For example, at K is equal to 10, we see that there is 0 tri-specialist, 1 quad specialist, 6 bi-specialists and 24 uni-specialists. So as you can see that as we keep increasing the value of K, the number of uni-specialists keep on increasing. Intuitively, we feel that if a user is a topper in one category, he is highly likely to be a topper in another category as well. Why? Because he is in general an enthusiast and performs good in all the activities. But that is not what we observed here. We can see that there are several uni-specialists and very few bi-specialists and negligibly few tri-specialists and quad specialists. It indicates that if a user was performing well in one category, he was not performing well in rest of the 3 categories. Of course, as we keep increasing the value of k, assume k is equal to 60, then in that case every user is likely to come in all the four categories, as in his name will appear 4 times in the list that we obtain. For example, if I post 59 questions, one answer, one insight and one pointer. Of course, when k is equal to 60 is taken, then my name will appear 4 times in the list that is obtained. But the point is that I posted 59 questions and only one annotation in all the other categories, so I'm expert in asking questions only. So it only makes sense to observe the behavior of users on smaller values of k. The figure shows the percentage distribution of the 4 types of categories. At a certain value, k is equal to 13. We observe that when 13 top performers from all the 4 categories are taken together, then out of these, 73% of the users show expertise only in one type of category. That is, they behave as uni-specialists. Moreover, only 2% of all the users post annotations in all the 4 categories. The figure also shows the percentage distribution in all other combinations of categories. For example, only 8% of all the users added both I-type and Q-type of annotations. Only 8% added both I-type and P-type annotations. Only 5% added both A-type and P-type annotations. And only 2% added both Q-type and A-type annotation. These observations indicate that the users show expertise in posting mostly one type of annotations only. For example, if a user is an expert in questioning, he shows very less expertise in answering, posting insights, and pointers. Based on this observation, we divided the users in various categories as per their expertise. Articulators are the users who keep adding their insights about the particular text that they're reading and help in better understanding of the text. Probers are the users who ask a lot of questions. They might indicate a class of users who have less knowledge of the given text, as well as people who are in general inquisitive and have this knack of asking good questions. Solvers are the users who answer the questions posted by others, as compared to the articulators who keep adding their knowledge even without having been asked any question. This type of users get into action only when they see a question. Explorers are the users who don't restrict themselves only to the current resource, but also keep looking for some relevant information outside the given text and make it available to everyone. We infer that these categories of users give rise to an ecosystem of categories in a knowledge building environment. Just like in an ecosystem, one species is responsible for the growth in another species. In a knowledge building ecosystem, the growth in the knowledge units of one category leads to the growth in the knowledge units of another category. Also, the presence of all the categories is equally important for the ecosystem to flourish. For example, if nobody is there to ask questions, nobody will add their answers to the knowledge building system. Therefore, the presence of people who can ask good questions is equally important for the knowledge building system. And that it is due to this ecosystem only, even the non-experts are able to contribute to the knowledge building process these days. After having witnessed the existence of ecosystem in crowdsourced and annotation systems, we conducted an analysis on the data of Wikipedia. The types of activities that the Wikipedia contributors perform are different from those performed by the users of an annotation system. We wanted to observe whether the users of Wikipedia performed a mixture of all these activities or they specialized in any one of them only. In order to check this, we analyzed the edit history of 10 Wikipedia articles from diverse areas. We examined the comments associated with top 5,000 edits for each article and observed that the main types of activities performed by the contributors were adding new text, making changes in the previously added text, updating the existing content with the latest information, reverting to the previous state, for example in case of vandalism, and providing references for the existing content. Based on this observation, we divided the contributors into editors, reverters, adders, updaters, and pointers respectively. The discussions taking place in the talk pages were not considered while forming the categories in this study, considering them to be the background actions happening due to the activities already considered. Now the goal was to identify the percentage of contributors that lie in more than one of these categories. The table shows for all 10 articles how many users participated as editors, reverters, adders, updaters, and pointers. This table shows all the 10C2 combinations of the 5 categories, that is 10 combinations for all 10 articles. For example, there were 28 users who participated both as editors as well as reverters in the Alan Turing article. This table shows all the 10C3 combinations of categories for all 10 articles. For example, there were 8 users who behaved as editor, reverter, and adder for the article Alan Turing. This table shows the scenario when 4 categories are put together. And this table shows the numbers when all 5 categories are put together. The plot shows the average percentage of users who participated in 2 categories, 3 categories, 4 categories, and 5 categories. As you can see that the percentage of contributors who performed 2 activities was 1.85%, those who performed 3 activities was 0.62%, those who performed 4 of these activities was 0.28%, and the contributors performing all 5 of these activities were only 0.17%. These plots indicate the percentage of users common in 2 activities, 3 activities, 4 activities, and all 5 activities for all 10 articles respectively. We clearly see that the number of people who perform more than one type of activity is very less, and the contributors specialize in one of the activities. This is significant evidence that the ecosystem exists in Wikipedia. In order to further verify this fact, we analyzed the data of Stack Overflow to check whether the ecosystem exists there or not. Stack Overflow is an example of a crowdsourced knowledge building portal based on discussion forums. It's a question and answer site for programmers. We analyzed the main kinds of activities that the users perform on this site. It was observed that the users mainly ask questions, answer the questions asked by others, read and vote others' questions or answers, or edit the questions posted by others. Based on this observation, we divided the users on the site into 4 categories: questioners, answerers, editors, and voters. In order to check whether the users participate more in one of the activities as compared to the other ones, we analyzed the top 500 performers in each category. Then we found the number of common users in these categories when 2 are taken together, 3 are taken together, and all 4 are taken together. It was observed that very few people participated in more than one activity. For example, as you can see the data, when top 500 questioners and top 500 answerers were taken together, only 23 users came twice in this list of 1000 users. This Venn diagram shows the number of common users in various combinations of the 4 categories. It can be seen that only 2 users participated in all the 4 categories. The figure shows that on an average, 3.72% of the people performed in 2 of the activities, 0.65% people performed in 3 of the activities, and only 0.1% of the users performed in all 4 categories. This indicates that categories of users exist in Stack Overflow as well. All these observations give rise to the inference that the users in any crowdsourced knowledge building portal can be divided into various categories based on what kind of activity they mostly perform on the portal. These categories then give rise to an ecosystem among the users of the knowledge building portal, where the users of one category trigger the users of other categories due to their different traits. We believe that due to the presence of this ecosystem only, knowledge building portals such as Wikipedia, Stack Overflow, and Quora have been flourishing and ever expanding. It's important to identify the categories of contributors and aid them to contribute better. The portal designers may employ strategies that identify the expertise of users and encourage them accordingly. For example, enabling a better display of questions to the solvers category would help them to contribute even better. Also, knowing that the presence of every category is essential in improving the knowledge building process, various incentivizing mechanisms can be introduced to further improve the engagement level of different types of users. Thank you for listening.